In this video, you will be learning about the Earth's energy balance. Energy that drives atmospheric processes comes from the Sun, and it is this energy that essentially establishes the temperature of the Earth's system. In fact, the only other energy source for the Earth is from decay of radioactive elements within the crust, and the continued cooling of the Earth from its hot primordial origin. These two latter Earth energy sources drive plate tectonic processes such as mountain building, volcanic activity, and earthquakes. As the title of the presentation indicates, and to anthropomorphize, the Earth seeks a balance between incoming and outgoing energy. This balance may be perturbed with a change in one of the parameters. This is the case with global climate change, where increases in atmospheric greenhouse gases from man's activities has resulted in a gradual warming of the planet. Starting with the basics, all objects, except for black holes, in the universe generate radiation depending on their temperature. This can be illustrated by looking at the different wavelengths of light that are released by the Sun. Note that the Sun looks different depending on the wavelength and hence energy and temperature of the spectrum. For example, in the visible wavelengths, the temperature is around 11,000 degrees Fahrenheit, whereas in the UV3 range, the temperature is much warmer at 270 million degrees Fahrenheit. We can also see this relationship on the graph of wavelength versus energy. In general, as the wavelength increases, the energy decreases. Note also on this graph that the Earth emits wavelengths in the infrared region, which is at a lower energy and temperature than the incoming radiation from the Sun. It is this energy, the infrared energy, not the incoming solar radiation, that is trapped by greenhouse gases and is responsible for the habitable temperatures that we find on Earth. Here is another view of the two radiation types. This map shows the amount of reflected shortwave radiation at the top of the atmosphere as detected by a satellite. The lighter colors indicate areas where short wavelength radiation or higher energy radiation is more reflected, and the darker areas indicate areas of less reflection of the shortwave radiation. There are several factors that contribute to the complex patterns evident on the map, including the amount of ice, the presence and types of clouds, and contrast between land and ocean. In this map from November 2013, the highly reflective areas are likely due to ice on Antarctica and the presence of clouds along the equator. Note that there is much less reflection in the Arctic areas due to the lack of solar input during this time of year. Now for the outgoing long-wave radiation for the same month detected at the same atmospheric level. Higher levels of long-wave radiation are prevalent in areas that reach higher temperatures and or have highly reflective surfaces like ice and desert areas. In this, the darker colors show the lowest amount of long-wave radiation, and the yellow colors show the highest amount of long-wave radiation being emitted from the top of the atmosphere. Note that these values are highest in the southern mid-latitudes, specifically along the western coast of South America, Africa, and Australia. These areas constitute desert areas, which are warm and therefore radiate more long-wave radiation. The darker blue areas at higher latitudes are with lower temperatures or have lower temperatures or heavy cloud cover that prevents long-wave radiation from escaping to the top of the atmosphere. Now let's look at another model for the Earth's energy balance. This slide shows a model for the different transfers of shortwave, high-energy ultraviolet radiation, shown in blue, and long-wave, lower-energy infrared radiation, shown in red, and two types of thermal energy, shown here in orange, that are exchanged in the atmosphere due to convection. This model assumes a beginning energy total of 100 units, which are usually recorded as milliwatts per meter squared. Now what is confusing about this model is that clearly the quantity of incoming radiation, 100, is not matched by the outgoing radiation. The The reason why is because the model shows the balance of energy for different parts of the atmospheric system. So let's walk through this model. This slide shows a table for the three different parts of the energy balance model. There are three parts: transfer at the top of the atmosphere, transfer within the atmosphere itself, and transfer at the Earth's surface. So let's walk through each of these. Let's look at incoming energy from the sun that is balanced with outgoing energy from the Earth. The total incoming radiation is 100 units. This is balanced by 23 units of outgoing shortwave energy that never reaches the Earth's surface. This energy is reflected by clouds. 7 units that is reflected from the Earth's surface. Note this is also shortwave radiation. 49 units of long wavelength energy that is reflected from the warming atmosphere. 9 units of long wave energy that is emitted by clouds. And 12 units of long wavelength energy that is emitted directly from Earth's surface to space. We do the arithmetic. It shows that the combination of short and long wave radiation at the top of the atmosphere are balanced. In this slide, the blue is meant to show the short wave, the blue numbers, the short wave radiation, and the red are the long wavelength radiation. So, this part of the model shows the values for the top of this table. The energy in the atmosphere itself. Blue is short wavelength radiation that has a higher frequency and higher energy, whereas red is long wave radiation that has a lower frequency and lower energy. The atmosphere absorbs 19 units directly from the sun. Clouds absorb another 4 units of the short wavelength energy. Long wavelength energy that is radiated from the Earth, which is the largest single source for warming the atmosphere, contributes 104 units of energy. 24 units of energy is provided by the latent heat of condensation during the phase change from water vapor to liquid water or solid ice, and 5 units are due to convection of warmer air to the atmosphere from the surface. These 5 input sources are balanced by 9 units of long wave radiation that are emitted by clouds, 49 units of long wave radiation emitted by the atmosphere, which escapes to space, and 98 units that is emitted by the atmosphere and returns to the Earth's surface. This process is the well-known greenhouse effect, where atmospheric gases absorb and re-emit energy to the Earth's surface. Without this process, Earth would be much, much colder. If you do the math, the inputs on the left are balanced by the outputs on the right. Note that all of the outputs are long wavelength radiation in the infrared area. So that takes care of the top two parts of the table. The final component of this model is to the Earth's surface. The Earth absorbs 47 units of short wavelength radiation directly from the sun, 8 units of long wavelength radiation that is re-emitted from the atmosphere. 116 units are re-emitted from the surface as long wave radiation, 104 back to the atmosphere, and 12 units directly to space. 24 units are distributed as thermal energy associated with water phase changes and convection. The mass shows a balance at the Earth's surface. So what are the take-home messages and connections to the work we'll be doing in this course? First, the atmosphere is a very complex system. Unraveling the energy balances requires detailed knowledge of processes that occur at all levels of the system. Second, the atmosphere and Earth system in general tends towards equilibrium. When one part of the system changes, the other portions respond to offset those changes. So, if the atmosphere absorbs more energy, then there is more re-emitted to the surface and temperature increases. This is what is occurring with global climate change driven by fossil fuel emissions. Third, for our work in weather, it is important to realize that weather phenomena is simply a method to redistribute energy through the Earth system. The main source of energy is not direct energy from the sun, but rather long-wave radiation and heat from the Earth, which is absorbed by greenhouse gases and then re-emitted by the atmosphere. And here are the references for my images. I hope this short lecture helps, and please let me know if you have any questions.